Okay, so one really interesting thing about exponential functions is that we were told in our basic definition that the base b could be any real number. And it turns out that there is one very interesting base discovered by, or well, named after, anyways, it might have been known before him, certainly known after, Leonhard Euler, that's how you pronounce it, a Swiss mathematician there, who found that this particular number, this is an irrational number, kind of like pi is an irrational number. It's a number that has a set of decimals that are non-repeating, non-terminating, just like pi. And so we would say that this particular number, this irrational number, can be used as the base of an exponential function. We call it the natural exponential function. Why natural? Well, it turns out that this base, this number e, is really based on something that Euler found, and this is actually looking a little bit ahead into your calculus class eventually that you'll take, and you'll find that there's a limit. And in this particular limit, it says that as n goes to infinity, the quantity 1 plus 1 over n raised to the nth power tends to be equal to the number e. And what I would advise you to do here is, I'm not going to work this all out, but please take a look at the table on page, what page is this? 352 of your textbook. And you can see what's happening right there. I'll pause for a second while you get your book, or you pause for a second while you get your book open. What that little table says is that it takes this quantity right here. It is the quantity 1 plus 1 over n, all raised to the power n, when n is equal to 1, or n is equal to 10, or when n is equal to 100, and so on. And if you were to take this value and just continue to open it up right here, you would find that, for example, at n equals 1, you're taking 1 plus 1 over 1 raised to the first power. Well, that's 2. At 10, you're going to take 1.1 raised to the 0.1 power, and that ends up being more like 2.59 something or other. And if you take 1/100th, right, n equals 100, you're going to get 1.01 raised to the 0.01. And you can work this out if you've got a calculator and a y to the x button. But you see what's going to happen right here is that eventually these numbers get closer and closer to this value named after Euler. Otherwise, it looks like a normal exponential function, right? Y equals 2.7183 raised to the power x. That is approximately 2e raised to the x. And if we compare it to some of our other functions, here I'll take this one, y equals 2 the x, and graph it just for comparison's sake, you can see it's really, really close. In fact, both graphs pass through the point 0, 1. The y value right here, here's the point 1, 2. Here's the point, we would consider this 1e. And if we were to look at the graph of y equals 3 to the x, we would see y equals 1, 3 right up above it right here. So this is really pretty close. It's between 2 and 3, right? Approximately, because e is an irrational number, we can say, well, it's between 2 and 3, closer to 3, right? And so that is where we picture this particular function's shape happening. And it turns out that this function is really, really interesting, especially this base, because we will use it later on to go through some examples where this is used to model all kinds of physical phenomenon, from population growth to radioactivity, decay, and all those other kind of things. So we find this to be an incredibly useful function, all named after this guy. Right, so Leonard Euler there, one of Professor Peoples' mathematical heroes. More to come.